there isn't any noise here to cause us problems?
So actually, you do not cause any noise, so you can keep your microphone unmuted. That's totally fine.
Okay, well, let's see how it goes. If I hear noise, I'll know it. So
Yeah,
I'll
and
try to
for
remember
others,
it.
please turn on your camera at least, because it's hard for me to interact with machine instead of humans. So yeah.
Well, is the camera on? Yeah, like my camera's on.
For others, like
Yes.
everyone else. So please turn on your cameras. It will be helpful for me at least.
My internet connection has been giving me troubles, so we'll see. I had new equipment put in a couple of weeks ago. I've had 50 interruptions since then. I'm keeping track of them because I have to try and solve this. But hopefully today will be good.
You're using is Spectrum Internet?
It's Opt Online, which is Altice or Altice. I don't know how you pronounce it.
Oh, okay.
It's Optimum. It's and you know, there's no competition, so that's the
yes,
problem.
that's the problem. Yeah. So here in Raleigh only we have Spectrum. Like if you have a secondary kind of connection, like they are also like taking Spectrum Internet and also distributing that. So that's why like Spectrum doesn't have any competition here. So that's a big problem for many.
Even in New York City, it's a problem. Where I did have Spectrum. I've disconnected it right now, but there, you have to get FiOS. It's the only other option, and that needs a piece of fiber optics to your place.
Yeah.
Okay.
Okay.
I'll show you.
So let's get started. Let's see, is everyone here so far? Almost. Okay. So what we were talking about last time, so we learned Lagrangian mechanics, right? So we started from Newton's law for system of particles. So Newton's law was like Fi equals to mi ai, right? And in principle, it has like if it has like constraint inside of it, then it has like degrees of freedom would be thrice n, or if it is d-dimensional system, then instead of 3 you have like dn, where this is the dimension of the space and this is the number of particles, right? So dn minus m, where this is number of constraints. So we actually converted this thing into we had actually, how many equations do we have here? Fi equals to mai, we had actually n equations. Remember, we had n piece of these equations. So we converted into small n pieces of this equation instead. Delta L over delta Qi, where Q is the coordinate, new coordinate, like generalized coordinate, equals to ddt of delta L over delta Qi dot. So you can like compare this thing into like F equal ma, because this piece is nothing but the force, and this piece is nothing but the momentum. So it's basically the same Newton's law written in a generalized coordinate form, or we are going to call it a covariant form. So it's in component form, but even if you change the coordinate, the form itself doesn't change this. So that's why we call it covariant. So there are other formulations of classical mechanics as well. There are 2 more formulations, but before going into those, we'll study Lagrangian mechanics a little bit further and understand what's deeper physics inside of it. So, so far, do you have any question? Do you guys have any questions so far? Okay, I hope there isn't any. I think there is.
Is it canonical momentum?
Yes, that the momentum, we usually call it canonical momentum.
Thank you.
Canonical means standard. Yeah. Okay. So to go into deeper in this physics, so we want to learn a little bit of new kind of mathematics. We call it calculus of variations. So usually calculus, it's already about variations, right? Changing things. So what's new to it? Like, what is calculus of variations? Can anyone answer? What's new to it? Why do we call it a different kind of calculus?
We deal with functionals here.
We deal with functionals here. Okay, yeah, that's a good answer. So basically, in ordinary calculus, what we do is we have a function. Function is basically a map, right? So function or map, function basically, let's call it as f. So this is a map. F is a map, and we have an input, which usually we call is that as independent variable. So let's call it x. So remember, x is a number. It's a purely number, right? So if it is a real calculus, then x is a real number. It sits somewhere on the real number line. And f is a map that takes that x as input and produces an output. That's again another number, say y. It also, if this is a real map, then y is also a number, like a real number. So in ordinary calculus, we study how this f changes over the input of x. So to find like maxima, minima, or kind of changing, we could actually plot it in our xy plane, right? Say we have a plot like this. Say our f of x can be represented like this. This is the representation of our map f. So here, what we are doing, we are actually changing our x a little bit every time and calculate, like finding that corresponding output value and plotting the corresponding like pair x and y, right?
Yeah.
So in this case, it's easy to find the maxima minima kind of situations like extremas, because we can notice one thing, like we change our x a little bit and reach at a point where when you change x a little bit, the function y, like the result of y, like the result of the map, that y, it doesn't change. So that's our maxima or minima point, right? You change your x a little bit, your y doesn't change. In the language of ordinary calculus, it's dy over dx, right? There is another notation, we call it f prime of x. So it's easy to understand and like it's easy to evaluate because we had a natural ordering between x. So we could actually make sure that we didn't miss any x we actually covered all the possible x values just by starting from negative infinity and going to positive infinity, right?
Yeah.
And they had a natural increment, like the natural ordering, so we could actually reach every x without any hurdle. But the problem arises when we deal with map that takes a whole map as another map as a input. So here in ordinary calculus it was like this, but in the new situation, like in calculus of variations, we have input that is okay. Let's oops. Okay, so there could be two scenarios. One is your map actually takes another map, like it could take a map and like let's write down something. Let's say your map is like denoted as big G, and your input itself is a map denoted as f and produces another number, say y. So in that case, we write this thing as y equals to g, a functional of f, not. So what does it mean? Like, what does it mean to take the whole function or whole map as an input? So consider a typical question. So what is the length of a particular curve? What is the length of a particular curve? So remember, the output length is
Integration of derivative square root over 1 plus derivative square.
yes. So the output is L, right? It's a number.
Yeah.
But input, is that input a number?
No.
You have to substitute or provide that that thing a whole curve, a whole map itself, right?
Yeah.
So for one curve, like say this one, your L would be something, and for another, your L would be something. You cannot input that thing like that. Say you have a functional, we call it. Let's say its operation is it produces L. That means the arc length. So to produce arc length, you need to produce like you need to provide it some arc or curve segment. You cannot provide it just a number, right?
Yeah, we are actually providing a branch of coordinates, I think.
No, you are providing a map.
Yeah, exactly. But you can think of providing a branch of coordinates too, and the coordinates actually define the function, the graph of the function actually.
Okay, okay. So does the coordinates itself define the a specific curve? No, you have to separate curve, not the coordinate.
Yeah.
So that what I mean is okay. We'll see example. So it's a little bit mathematical abstraction. Then it will become apparent in a moment. So this is one scenario. So you provide a map itself. This big G map, it produces a number, but there could be another scenario that some big H, it's that functional map, it takes a map and produces another map. So that could be a possibility. So we actually saw this kind of example already. So let's talk about that. So we learned our Laplace transformation, right?
Yeah.
So what was Laplace transformation? So we input, like we provided it this thing as some map. say f of t defined as, let's say, e to the power negative t or sine t, like that, right? So we provided f and we produced what? Big F of this thing, right? But it was a function of s, so it was defined like integration 0 up to infinity f of t e to the power negative ts ds, like that. So when you perform the sorry, it was integration over t, right? So when you perform the integration over t, this thing becomes like a function of s. The whole thing becomes a function of s. That's true. So this thing has two properties. So it's a function of s, but a functional of f. Or in this notation, instead of curly bracket, we write it like this. So it's a functional of f. So if you change the input, if you change the function, that function or map that you have provided, the output is changed. But output is also a function. So you provide a map, it produces a new map, or instead it could produce a number instead. So let's see an example. So let's ask, what is the distance, like what is the arc length from on this plane from this point to that point. Let's denote this thing as x1 y1 to x2 y2. So what would be the arc length from here to there?
I need a function.
You need a function, right? So you need to provide something that connects these 2 points, right?
Yeah.
So let's say that thing is like small g of x, y equals to a small g of x. That's this curve. So then what's the arc length?
Integration.
So arc length L, which is a number just, that would be integration over x1 up to x2.
Root of 1
square root of
plus
1 plus
y prime square or dy dx square.
Okay, actually for everyone, let's not just write down the expression, we'll just derive it, right? So what would happen, like say we have a small piece here that has an arc length ds. So we need to write that ds in terms of x and y. So if we apply Pythagorean triangle, so that ds could be written as square root of dx square plus dy square, right?
Yeah.
So now what we can do, we can actually factor out that dx out of this integration. So that becomes x1 up to x2 square root of 1, because we have factored out dx. So 1 plus dy by dx whole squared dx, right? This is what you are trying to say, right? Then in terms of function, we have to write it like this. In terms of the input function, so x1 up to x2 square root of 1 plus g prime of x dx. So if you change your g, the function itself, squared, so if you change your function g, then g prime is also changed. So this integration produces a value that is something else. So you can supply this one, you could supply another one, like say f of x, you could supply another one like h of x. So for every function, when you supply here, you get a different number. So that's what we mean by a functional, right?
Yeah.
Okay, so now there is a $1,000,000 question. So what is the curve? What is the shape of the curve g of x? Like for what g of x this length is minimum?
It's a straight line just for a plane. It's a straight line.
So how do you know without doing it?
Uh, Using variational calculus.
Yeah, that's what we are trying to do.
Yeah.
We haven't studied that yet. So question is, so to do that, like parallel to the classical ordinary calculus, what we need to do, we need to supply different function and test what the number is, right? But
Yeah.
we have to make sure that we have supplied all functions and tested every functions.
Yeah.
So, but the problem is the functions like the maps g of x, it doesn't have any natural ordering like the number x.
Yeah. Not an ordered set. Yeah.
Yes, it's not an ordered set. So we do not have natural ordering, so we cannot make sure that easily that we have tested for all functions g of x. So that's why we need to make a trick over here. So the trick is construct a natural ordering out of it. That's the basic goal here. Construct a natural ordering out of it.
Yeah.
Okay. So let's go to the generic situation. So let's talk about that arc length again. So arc length L, or small l, I could write. Arc length is small l. It was x1 up to x2 square root of 1 plus g prime of x whole squared, right?
Yeah.
So this is one problem. So let's talk about another problem. On xy plane, you have like a position dependent refractive index eta xy. Refractive index in optics, it's defined as the light speed in the vacuum, and like the ratio between the light speed in the vacuum, that's c, and the light speed in that point. This is the definition of eta. So question is, if a light beam starts from here and ends up being here, so what path actually it took? That's the question. It could take this way, that way. So from one principle in optics, we know, Fermat's principle, we know that light takes the path that that takes the minimum, like shortest time to travel, right?
Yeah.
So if the light beam started from here and ended up being here, then it should have taken that path that took the smallest amount of time. So in terms of this expression eta, what would be the time needed by that light? So obviously integration, that starting point up to ending point dt. Actually, mathematically speaking, like the time at x1 and time at x2, but for the moment we just understand it.
x1, y1 to x2, y2.
Okay, but also like t at x1, y1, that you have to write, because you're integrating. So you have to write. So usually in textbook you'll just see just 1 and 2. So by 1 and 2 means when you have a variable t at point 1, you have to consider that t at 1 and t at 2 over there. Also when it has like dx, then x at 1, that at x at 2, like that. So don't worry about it. We all know what it means. So okay. Definitely we are not going to do like, okay, if we integrate this thing, it becomes like t, and 2 equal to 1. No, 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 we are not going to do that. Okay, so in terms of velocity or speed v, it's not velocity, it's basically the speed. So we can write it as this: distance divided by speed at that point, right?
Yeah.
X, y. So it can be written as instead of like v, we can substitute eta over there, and we find integration 1 up to 2
ds by mu,
x
1 by c.
ds, right?
Yeah.
So again, like in the last arc length problem, ds was square root of ds is infinitesimal distance that it traveled,
Yeah,
right?
it is
So
root over
we can
1.
write in terms of those x and y, right? So that would be square root of dx squared plus dy squared. So we can write it as like 1 up to 2 eta of xy divided by c square root of 1 plus y prime, we could write y prime dx, y prime squared dx.
Yes.
So let's look into the argument. So here, like integrand. So here the integrand is this thing. So it depends on, it's a function of, the integrand is a function, let's say u of is a function of x, that's okay. It's a function of y, that's fine, and also a function of y prime.
Yes.
It has this
Yeah.
form. So for arc length also we had this form, but xy didn't appear explicitly. So here for arc length we could write it as like integration, some function of just g prime. But in principle, like we could add those as well, right? So this kind of problem, it has a generic structure that we are trying to find, we are trying to extremize a function, extremize a number, some s, that has a form integration over some limit, say x1 up to x2. And inside of that, we have a function of independent variable, dependent variable, and derivative of dependent variable. This is structure. So in general, we are trying to extremize this kind of functions, functionals. Actually, functional could be more general, but we are actually interested in this particular type. In dynamics, we are actually interested in this particular type.
Yes.
It could be more general, like a functional in principle, like a generic functional. So could be like it could be like this: e to the power integration x1 up to x2 some f of blah 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 dx. It could be like that. But we are not interested in this kind of functionals. We are interested only this type of functionals, because that's relevant to our dynamical systems. Okay, so we are actually changing, like this s formally written as it's a functional of y, right? It's a functional of y. Y is a map actually that takes x as an input and produces a number.
Yeah.
So we write it like this. And remember, there is a standard notation that usually we start with dependent variable, derivative of dependent variable, and with a semicolon we write the independent variable. This is the standard notation because we usually separate those two. Otherwise, if you write like this, you could confuse easily. So this is the standard way of writing, like dependent variables first, then semicolon, independent variable. There is a reason, because in many integral independent variable, it doesn't appear explicitly. So many times, like someone could write f of y prime only. But usually you should consider this. So we are trying to extremize this kind of function. So all you need to vary your y. That's our goal, right? We need to vary our y. So is there any questions so far?
Y and y prime are independent of each other.
Yes, that's fine, but you are providing y, so, and you can like formally you have your y prime when you supply your y, right?
Yeah.
So yeah, at a specific point, y and y prime are independent, but when you're talking about the whole map, they are not. So when you're talking about a map, say this thing, then when you have provided that, slope at this point is already determined. Okay, but when you're talking about just a specific point, then a curve passing through that point, it could have like same value but with different slope. So you need to understand like in which context they are independent. So when we're talking about point-wise situation, then they are independent.
But we are talking about functionals. They are taking map as an input. So
They're taking the whole curve as an input.
Yeah, when I have given a curve as input, so I have given a curve. So the derivative of that curve is defined at a point.
Yes, you have already provided that.
Yeah. My question is, if there is there's input, the function is, or the curve or the map I have given as an input. So I have given a y prime. Isn't
yeah, when you have provided
y as point
y prime. So let's say you have provided y equals to x squared. You have already provided your y prime equals to twice x, and there is no confusion about it. But when you're talking about varying that functional at a specific point, let's say you have provided that, that's fine. So okay, that's the wrong curve I drawn. Let's draw the correct one. So this would be the correct one, right? Y equals to x squared. So let's talk about this point. So at this point, you could actually vary your curve as well. So it could have a like a specific value at that point, but you could pick a different curve that goes like this.
Yeah, got it.
So when you're talking point wise, then they're independent.
Yeah.
Okay. Okay, so let's vary it. So how do we vary? So we have this kind of diagram for let's say this is our y that produces the minimum condition. So when we vary it a little bit, say with a different path, different curve, like that one. So let's call it big Y instead of small y. So big Y of x, it's written as say y of x plus some eta eta is not a refractive index, eta is a function again, like that. We can write it like this, right? And also we need to impose some constraint on eta as well. So eta of x1, it has to be equal to 0, otherwise they would not match at this point. Also eta at x2 has to be equal to 0, otherwise they would not match at this point. Because those both curves passes through the same initial and final points. Okay, so we could write like that.
Yeah.
So now, if you multiply this thing by another number, some alpha, and that varying by alpha from 0 to infinity, you could actually achieve many more kind of functions out of this generic function y of x. So you multiply by a number alpha and you vary that number. So our big Y is actually a function of two things. One is a function of x, that's fine, also a function of alpha. When alpha equals to 0, remember y at x0, right? Y at alpha equals to y at x0, which is equals to just y of x. Remember that.
Yeah.
So why did we do that? It produces a natural ordering between a specific class of functions. So any function that is basically an addition of y of x to something that can have an ordering. So you just vary those alpha from, say, negative infinity to positive infinity. So you actually varying this y of x without missing any. So any function that can be written in this form, like that y of x plus something, in this specific form, any function that can be. So you are actually varying using just one parameter, that is alpha. So that gives us a natural ordering between at least one class of functions.
Is it a constant? Here on a constant function.
Y eta of x? Yeah, it's a function. What do you mean by constant function?
I mean specific function.
It's a specified function, right? Yeah. Eta of x is a specific function. Yeah.
But we can make any kind of function capital Y of x using this Y of x and alpha eta of x.
No. You cannot actually. You cannot, like, for a specific kind of eta and specific y, you cannot make any arbitrary function. Remember that.
Not a specific eta.
Oh, for arbitrary eta,
I can make
yeah,
any
you can actually achieve any function you want for arbitrary eta.
Okay. Thank you.
So that's also a problem, because we do not have a natural ordering between all etas, right?
Yeah.
So, like, talking about varying eta itself, that's a problematic case. So we somehow want to avoid that kind of thing, and luckily we have that kind of situation in our hand that we can avoid eta, like varying eta itself. Why? We'll see later. See in a moment, actually. So let's do it. What we're gonna do, we are actually going to find the change in S for two situations. So in principle, actually, we can write S if you supply as big Y, which is a function of x and et alpha. So we can write it like x1 up to x2 if big Y prime and x dx, right? Now remember, we are integrating only over x, but this thing had an argument alpha inside of it. So this whole functional, it's a functional of y, but now it's a function of alpha as well, right? Because you change the alpha, you change the number here, like change the output here. So we are going to write like that.
Yes.
Yeah. So it's integrating over x. So alpha is still there, right? You can change your alpha and find a different number for each of the s. So in this case, you have your ds over d alpha defined because alpha is a number, s is also a number here.
Yeah.
Okay, so which situation are we trying to find? So we are trying to find a situation when we change our alpha a little bit, but that s doesn't change, right?
Yes.
So that would be ds over d alpha equals to 0, but we are actually fixing our alpha to be 0 as well. Why? Because when we are actually fix our alpha to be 0, then we get our y of x, right?
Yeah.
So we do the calculation, we set finally this thing. This is our desired condition that we want to impose on that thing.
Yeah.
Yes.
Okay, so let's proceed and do that. So let's write it again. What would be our ds over d alpha? Let's evaluate that first. ds over d alpha would be dd alpha of integration over x1 up to x2 f of big Y prime and x dx, right?
Yeah.
So
Del
what
F
was
del
our
alpha.
big Y? What was our big Y? Big Y of x comma alpha, it was, remember, it was small y of x plus alpha multiplied by eta of x, right?
Yeah.
Where eta had some initial specific condition, like specific initial condition that was eta at x1 equals to 0 equals to eta at x2. That we had imposed, otherwise they would not match at the endpoints. Okay, so now we can actually take this derivative inside of the integration, because integration is running over x, but differentiation is running over alpha.
I have a question.
Sure.
I think alpha is an independent variable. Am I right?
Yes, x and alpha are independent. You can change your x and alpha totally independently.
Yeah. So shouldn't we include alpha as an independent variable with x?
No. Like, does that alpha appears explicitly in your f? No, it appears through y only.
Yes, but y is not completely dependent on x only. Y also depends on.
Actually, it is capital Y, not the small y.
If it's
Yeah.
not small y, so capital Y, like alpha, doesn't appear explicitly in f. Like here, x could appear explicitly here. That's why you included that. But alpha only appears through y, not directly.
Okay. Okay. In that case, capital Y should also be independent because it is not completely dependent on x. I mean, we are not including alpha as the independent variable. We are also not including y as the independent variable. But there are two independent variables here. That's what I'm concerned about.
Oh, okay. So you are talking that this y of x, it's an independent variable, like that kind of thing?
No, not that one. The capital one. The capital Y. The capital Y should be independent. I mean, not completely independent, but it is not completely dependent on x only. That's what I'm saying.
Yeah. So if you have if you are uncomfortable with this notation, you should write it more explicit notation. That is f of big Y of x comma alpha y prime of x comma alpha comma semicolon x. Are you happy now?
What I was trying to say is that capital
Yeah, I
Y.
understand. You're trying to say like I should include my alpha over here, right?
Yeah, that's okay. Or I can include the capital Y beside x as an independent variable, because Y is not completely dependent on x only. I mean, I'm trying to say that there are
This
independent
is
variables.
big Y. This is big Y. This is capital Y.
Yeah, the capital Y is not dependent on x only. It is also dependent on alpha. So I think there should be two independent variables. That's what I'm trying to say.
No. point is, yeah, there are two independent variables here, x and alpha, that's fine. But this function inside of this, like f of something, this only depends explicitly on x, not explicitly on alpha. F depends on alpha, but that only through y, not directly.
For example, I can say when I wrote
Yeah,
root
let's
over 1 plus y prime square, that y was
so,
actually capital Y here.
so no, let me give you an example. Like here, our refractive index was like position dependent. X was an explicit thing that appeared here. It appeared explicitly. Like our eta would have a relation like x squared plus y, like that. But this thing cannot depend on alpha, because alpha is our mathematical construction. That's not a real thing.
I have to replace y prime square, small y prime square by capital Y prime square, right?
Yes. Yes.
Okay, that's why alpha is not coming here explicitly.
Yeah. Alpha was never there actually. Alpha was never there explicitly. We constructed alpha.
Yeah.
It was never there. We just changed our y to big Y. That's all. And alpha got introduced there, like inside of big Y. So are you convinced, or I need to give you more example?
I'm not actually convinced, but I think we can continue. I'll just repeat later. We can continue, I think. I don't think it will matter. I don't think it will matter.
It will matter if you, yeah, like this f, it was never dependent on alpha itself. So why you are like taking your some alpha like out of nowhere here? So we just replaced y by big Y. That's why it appeared over there.
I mean, I think that it's okay, but I'm just trying to say that there should be two independent variables. That's all I'm trying to say.
Yes, there are, but those two independent variables are not same.
Yeah, they are not same. One is x and another one is alpha, which is included in y.
Yes, 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 that's true. X can appear explicitly here, but alpha cannot appear explicitly here.
We can think of it like this. If say for example f is a function like y plus y prime plus x, what we are doing actually is just replacing those small y by capital Y. So if small y had value y is equal to 1, y prime is equal to 2, and x is equal to 3, then the function will have value 5, right? But if you are replacing capital Y prime, and x, capital Y, substitute capital Y for 1, capital Y prime for 2, and x is equal to 3, and the functional value will still be 5.
Yeah, I think f can be written as a function of y prime and x. I think that's all right.
Okay, let's continue. So basically one independent variable can appear explicitly, and another is like that only appears through our mathematical construction, that big Y. Okay, so take that derivative inside of it. Now integration x1 up to x2. So when you take that differentiation under integration sign, remember this thing can be a function of x as well. So we have to write it as delta delta alpha, not just dd alpha, right?
Yeah.
So now using multivariable chain rule, Using multivariable chain rule, we can write like this. Delta F, alpha never appears explicitly. So delta F over delta alpha, it means delta F over delta y by delta alpha, because alpha only comes through y, not explicitly, plus delta F over delta y prime over delta alpha dx.
Yeah.
Okay, great. So now we need to we need to explicitly evaluate delta y over delta alpha and also delta y prime over delta alpha. So let's evaluate it from here. So if you evaluate your y prime means derivative with respect to x only, not alpha. So y prime equals to small y prime of x plus alpha eta prime of x. And if you take derivative with respect to y, that means the derivative with respect to alpha, so delta y over delta alpha, it would give you, here take derivative, it will give you just eta of x, right? And similarly, delta y prime over delta alpha would give you eta prime of x. Happy?
Yeah.
Take differentiation with that. So we can substitute those things over there. And we have integration x1 up to x2, delta f over delta y, eta of x plus delta f over delta big y prime, eta prime of x dx, like that. Now perform an integration by parts. Keeping this part fixed. So just leave that as it is. And perform an integration by parts on the second part. So if you do an integration by parts, so integrate this part and keep that part as it is. So delta f over delta y prime. And if you integrate eta of x prime, then you get eta of x evaluated at x1 and x2 minus, now you kept this part, so now you need to differentiate that part. So integration x1 up to x2 ddx of delta f over delta y prime, and integrate that other part. So like eta prime of x gives you eta of x dx. This is the result of our integration by parts.
Yeah.
So question
The boundary
is, what is this?
is 0.
Yeah. What do you get when you substitute your boundary?
Yeah. Eta x1 is equal to eta x2 is equal to 0. So
yes, eta at x1 equals to 0, also eta at x2 equals to 0. So on both limit, upper and lower limit, this part gives you 0, right?
yeah.
So everyone on the same page?
Yeah.
Yes.
So we get integration x1 up to x2 delta f over delta big Y minus ddx of delta f over delta big Y prime eta of x dx. So this is the result of our ds over d alpha.
Yes.
We need to set, remember, to extremize this situation, we needed this thing like delta s over delta alpha at alpha equals to 0 equals to 0.
Yes.
So first evaluate ds over d alpha at alpha equals to 0. So ds over d alpha at alpha equals to 0 gives you integration x1 up to x2. What's the change should be here?
Capital Y will be a small y.
Yes, when alpha equals to 0, big Y becomes small y. at alpha equals to 0, right? So all we need to write it like this: delta f over delta small y minus ddx delta f over delta y prime eta of x dx. And if we set this thing to be 0, that's the condition of extrema. So eta, it's an arbitrary variational function, right? Arbitrary function. It cannot be 0. And this integration has an arbitrary limit. So x1 and x2 could be anything. So if an integration is 0 for an arbitrary limit, that only one thing means that integrand has to be 0. This thing has to be 0. But eta is an arbitrary function. It cannot be 0, obviously, in general. So the only thing left is delta f over delta y minus ddx of delta f over delta y prime. This thing has to be 0. So this is the condition of extremization of S.
Yeah, same as Latin. Yeah.
So the statement, now the statement finally. So if you have a functional of the form this, that is integration x1 up to x2 f of y prime, f of y prime, and most possibly x dx, then ds over d alpha at alpha equals to 0, this actually in shorthand notation written as variation of S, this thing equals to 0. Okay, so if you have this thing, if you have S defined like this, then variation of S automatically implies delta f over delta y equals to ddx delta f over delta y prime. Happy?
Yeah.
And also it goes in both ways. Like if you have an equation that looks like this, then you could always find a functional that looks like this one, right? So does this equation looks familiar? Does it look familiar?
Yeah, like Lagrange equation.
Lagrange equation, yes. So remember, there is a distinction between those two. So this is called Euler-Lagrange equation. Euler-Lagrange equation, EL equation. Euler-Lagrange equation is purely mathematical. So it has nothing to do with dynamics itself. But in dynamics, we found an equation, the Lagrange equation, that looks like this. So instead of F, we had L. Instead of Y, we had the coordinates. And instead of independent variable, we had time, right?
Yes.
So automatically we can construct something like this out of here, right? So what would be our S here? What would be the corresponding
Action.
We call it action. The corresponding S would be T1 up to integration T1 up to T2.
Yeah. Yeah.
L
DT.
that is a function of QI, that means function of coordinates, derivative of coordinates, and most possibly the independent variable itself, dt. And if you define your S like this, then variation of S equals to 0 automatically gives you Euler-Lagrange equation. Because of the same construction, like you do the same calculation for starting like this, just same different notation, that's all, right? So what we found that for our Newton's law automatically gives rise to the Lagrange's equation, right? And Lagrange's equation has a form of Euler-Lagrange equation. So we can always construct some quantity, we call it action, that is basically an integration of Lagrangian over time. And our dynamical system, like the equation of motion, is automatically produced then if you just set our variation of S to be 0. So in the physics wise, we can say that for every mechanical system, there exists some quantity, we call it action, but there's some quantity, we do not know what it is, whose variation is 0, which means the mechanical system always tries, or mechanical system behaves such as that quantity, that action is extremized.
Yes.
So any questions so far?
No.
Can you just repeat the last thing?
Okay.
Yes.
So for every mechanical system, you can construct some quantity S, like this equation, like using this equation, of which variation is 0, gives rise to the equation of motion. Or in other way, your system behaves such as that quantity is extremized. Like you start some motion, like you throw two objects, they gravitationally interact or something, they moves or something, but they move such a way that action quantity is always minimized or extremized. Actually, it could be maximized as well.
Okay.
The system always tries to extremize S. That's all. Usually it minimizes, but it could do the maximization as well.
Got it.
But we had to consider only a class of function or a class of curves. What about that?
Okay. Yes. So we could not use every possible variations, right?
Yeah.
So we can achieve every possible variation by changing eta of y, right? Eta of x.
Yeah.
And interestingly, it did not appear explicitly in the EL equation. So
yeah, got it.
It doesn't matter, you change it. So we kind of got rid of that uncomfortable eta of x.
Is this a thing that when we add some time derivative in Lagrangian, the total thing does not change? You told me the previous class.
Yes, that's
is
the
this
result
a
of
thing?
Yes. So let's prove it again. So let's define our new defined action S bar such that S plus some number. So number, let's call it A. So how A is defined? A is just a number. So we write T1 up to T2 L dt, and A is defined T1 up to T2 df over dt dt. Or actually, I should write this as f, some number. Okay, no, it might confuse you. So let's write it A. So by integrating this thing, we get A equals to f at T2 minus f at T1, right?
Yes.
So A is just a number. It's not a function. It's a purely number. So extremizing S and extremizing S bar are same thing, right?
Yes.
A is not a functional as well. So you could extremize any of those, like S or S bar, and get the same equation of motion. So that's why actually this adding, like you could write this thing as integration T1 up to T2 L plus df over df over dt dt, like this. That's why adding df over dt to L doesn't matter when f is a function of q and t only, remember.
Yes.
Okay, so one last proof is that our Newton's law is equivalent to this one. Newton's law and this one are equivalent. That's what we are going to prove for mechanical systems. So we'll consider Newton's law, like F equal ma, to be true. We'll consider this to be true and prove this one. Okay.
Yes.
Where is the cursor? I don't see it. Oh, it's here. Okay.
Can we take a break for
Oh,
a few minutes?
yes. Already, yeah, 1 hour. Okay, let's take a 10-minute break and come back. Thank you for reminding me. So if